Thank you. Thank you for the introduction. It's a pleasure to give a talk at this workshop. I'm going to tell you about perfect embeddings of the hexagon. This is a joint project with Thomas Berggren and Matthew Nicoletti. Both are at MIT right now. We already have a very nice introduction during the first talk about the dimer model, so I'll just briefly remind a couple of definitions which I need. We're interested in general, we're interested in dimer model on planar bipartite graphs. Planar means we can draw it without overlaps. Bipartite, that vertices can be colored in black and white, such that every two adjacent vertices are different colors. And we're interested in dimer covers of this graph. One of them is shown in blue on this picture. And two prototypical examples are dimer model on the square lattice and on the hexagonal lattice. It is clear from this picture that instead of dimer configuration, let's say on a square lattice, I can think about domino tilings of the domain on the dual lattice. And note that for the case of the hexagonal lattice, the dual lattice is triangle lattice, and here we're interested in lozenge tilings of the discrete domain, where lozenge is a union of two triangles. All right, so dimer model is a random measure on dimer configurations. So let me quickly remind you what is the definition. So in general, we have a weight function on the set of edges. So we assign a real positive value to each edge, and we say that the probability of each dimer configuration is proportional to its weight, where the weight is simply the product of the corresponding edge weights. And you need to normalize it by a so-called partition function, which is the sum of those weights over all dimer configuration. You can easily convince yourself that for this example, there are exactly 3 of them, and this is a partition function. All right, this is a quick reminder. So one of the main tools and important objects in the dimer model is a Kestelian matrix. So what it is, to define a Kestelian matrix, I first need to define the Kestelian signs. We know that for the bipartite graph, every face has even degree. So we say that we put some signs or complex signs. So those are complex numbers with modulus 1. And we want them to satisfy the Kestelian sign condition, which is along each face, the alternating product of the signs is plus or minus 1, depending on the degree of this face. And as soon as you have these signs, we define the corresponding Kestelian weight, which is the product of the edge weight times the sign. And now we take this Kestelian matrix, which is adjacency matrix. Actually, it's a quarter of the adjacency matrix, because I want to deal with a matrix whose rows index the white vertices and columns index the black ones. And then it's known that the partition function can be given in terms of is actually the determinant of this Kestelian matrix. And moreover, all local statistics can be computed in terms of the inverse Kestelian matrix. All right. Today, mostly, I will focus on the hexagon, uniformly weighted hexagon. We even saw a couple of pictures already this morning. So we have a regular hexagon on the hexagonal lattice with the same length of each edge. On this example, it has 4, and the corresponding hexagon and the lozenge tiling on this side. Right, one of the interesting questions is how the typical random lozenge tiling look like at the large scale, and it is known that it satisfies so-called limit shape phenomena, so you have these frozen pieces close to the corners. For the hexagonal lattice, there is a very natural definition of the height function, which we already saw in the morning for the square lattice. Note that you can think about this picture as the 3D picture. Hopefully, all of you can see it. And more precisely, it's actually a projection of the surface in 3D. So we can think about this as a orthogonal projection of the step surface in the R3 with vertices at Z3. And then we think about the height function, which define at each vertex as a distance between the projection and the real surface itself. In general, we want to deal with the integer valued surface, so like you need to multiply it by square root of 3. Here is another way to define the height function in case you don't see the 3D picture on this one. You can forget about that. Take a chessboard coloring on the triangular lattice, and we can define the height function, which is following some rules when you go along each edge, depending on the color of the on the sides of the of this edge. All right. So now, instead of the lozenge tiling, we might be interested in these surfaces in 3D. And one of the main questions is related to the limit shape. And the next question, natural question about the fluctuations, if we already know the limit shape, how much it fluctuates around the surface. And the limit shape for the hexagon is known. We already, it was mentioned during the first talk that there is the variational principle, and there is a hard question how to identify this surface in general. It is known in case of the hexagon, so we know the limit shape. So how to think about it is like the normalized height function approximates some deterministic surface. In other words, like the local density of each type of those lozenges converges to a deterministic limit. And we call the liquid region the region where those densities are strictly between 0 and 1. All right, so I'm mostly interested in the question of the fluctuations, convergence of fluctuations during this talk. It is also known, this is a result by Leo Petrov, that in the case of the uniformly weighted hexagon, the fluctuations inside the liquid region converge to the Gaussian free field, but in a new conformal structure. So we take a liquid region, which is known to be just a disk, and we map it. There is a precise map. The only thing which you need to know about this map right now is that this is not a conformal map. So we need to change the conformal structure to get the Gaussian free field. What we get the Gaussian free field is these new coordinates, in these new complex coordinates. Right. I don't think that I need to give a definition of the Gaussian free field here, but very quickly, so this is the random distribution where the covariance is given in terms of the green function, and this is one of the places where the complex structure appear. We need it for the green function. All right. So this is what is known. What is new? I'm going to tell you how to construct the perfect t-embedding for the uniformly weighted Aztec diamond. And another result is that perfect t-embeddings converge to the maximal surfaces in the Minkowski space R21. Don't worry, I will explain what is a perfect embedding in a few minutes. Right now, I'm just mentioning what are the main results. And as a consequence from this result, we get a different proof of the convergence to the Gaussian free field. But what is more important about that is that we get a new definition, new description of the conformal structure in which those fluctuations converge to GFF. OK. Right. Let me tell you what are those embeddings. So as I said in the beginning, in general, we're interested in planar bipartite graphs. So they are already embedded, but I'm not happy with it. I want to redraw those embeddings in a different way. What might be the reason? One of them is, let us think about this piece of the square lattice. And as I said, in general, we deal with weighted dimers. So we have weights on each edge. And if I just take the regular square lattice, those weights are just real numbers on edges. There is no geometrical meaning. At least there is no geometrical meaning of those weights on edges. Could I give some geometrical meanings to those? Like, could I redraw a graph in such a way that maybe the length of this edge is given by this weight, or some other connection, some other interpretation of those geometric of those weights in a geometric way? Also note, which is crucial for me today, is that edges and dual edges are in bijection. And instead of thinking about geometrical meaning of the edge itself, I can think about the dual edge. And maybe I can think about the length of this dual edge, and I give the geometrical interpretation of those real weights in terms of the length of dual edge. And now, instead of dimer configurations, I'm thinking about tilings, where each tiling is just the union of one black and one white face. All right, so another question, another motivation, as I mentioned before, to get the Gaussian free field, we need to change the conformal structure in the limit. What if we redraw graph from a very beginning in such a way that these already give us a correct conformal structure? Could we do this? And this is the, we believe that yes, answers to all of those questions is yes, and I'm going to talk about two joint projects in the next couple of slides, which are related to those questions. Okay, so before that, let me talk about the gauge equivalent weights, because this is important for us. So one more definition, sorry for that. Note that if I have a weight function, and I multiply all weights around one vertex by the same constant, then the probability measure doesn't change, right? Because each dimer configuration should cover this vertex, so we take exactly one of those edges in a dimer configuration. So each weight of each dimer configuration is going to be multiplied by this number, by this constant. So same happened with the partition function, so the probability measure doesn't change. So we can think about these weights on edges up to a sequence of such multiplications. So more precisely, we say that two weight functions edges are gauge equivalent if we can define two functions. Recall that our graph is bipartite, so I can think about them as two functions, one defined on black vertices, another defined on white vertices, such that the first weight function is given in terms of the second weight function by multiplication of those functions at the ends of the corresponding edge. Okay? And yet again, note that the weights which are gauge equivalent define the same probability measure. So now I'm thinking about my weights on edges up to a gauge transformation. And I'm asking whether I can redraw a graph in such a way. I'm actually going to embed the dual graph. So I want to draw the embedding of the dual graph in such a way that the lengths of the dual edges are gauge equivalent to the initial weights on edges. This is one of our goals. Another thing is that I want a proper embedding, so no overlaps. It should be a proper embedding to the plane. And we also ask the angle condition, which is the following. Around each vertex, we ask that the sum of black angles is the same as the sum of white angles. And of course, both of them are pi. Okay? So this is what I call a t-embedding. So if we start with a bipartite graph with weights on edges, and now we want an embedding which gives us length of edges, give gauge equivalent weights, and they satisfy the angle condition. All right, so why do we want this angle condition? I will explain in a second that this allows us to define not just the weights in a geometrical way, but together with the Kästlin signs, which I was talking before. But before we go there, I want to also define the origami map. So what we're actually going to do, instead of embedding the dual graph to the plane, we're going to embed the dual graph to R2 plus 2 Minkowski space. So we're going to have two coordinates. One of the coordinates is the t-embedding, which I just explained. But together with it, we have the second coordinates, which is an origami map. So what is an origami map? Starting from a t-embedding, this angle condition allows us to do the origami with this. So you can literally fold the t-embedding along each edge. And what you get, we call the origami map. So now I take the positions of these vertices, which correspond to the position of these vertices, which remember were vertices of the dual graph in the beginning. So to convince you that you all actually understand well the definition, let us think about your favorite origami. Probably all of you did it at some point. So here is a paper plane, right? I make it planar, so now it's, I think, in the complex plane, and I take the positions of vertices as the positions of the origami map. Now, if you unfold this paper plane or any other origami which you like, you have these lines of the folding, right? You have the segments of the foldings. And now if you color the faces in chessboard coloring, I did it for you, you get a t-embedding. So indeed, around each vertex, the sum of black angles is equal to the sum of white angles. And this is what allows you to like literally do this around each vertex, so you can fold it. So OK, I start with my t-embedding. Here is, hold on, I need it back. Could I do it? So this is my t-embedding. This is a corresponding origami map. Of course, origami map is defined up to a translation and rotation, right? I can decide that like I fix the position of, let's say, this face, so I can glue it here, and then it defines my origami map uniquely as soon as I did this. So I hope that now the definition is clear. We have two objects. One is the t-embedding. Another one is the origami map. This is not true that you always can fold a piece of paper starting from a t-embedding, because you need to deal with layers. And here I deal with a map from the complex plane to the complex plane. However, around each vertex, this is true that you can always fold it. OK, so all right, now we have two coordinates. One is a t-embedding, another is an origami map. And note that it's actually the origami map is a Lipschitz map, clearly because of this folding. The length is smaller than the initial length of any 2 points in the t-embedding. So we get a discrete space-like surface in the Minkowski space R2 plus 2. So I want to think about embeddings actually not to the complex plane, but to the R2 plus 2 Minkowski space, where yet again we have two coordinates. One is a t-embedding, and another one is the origami map. All right, any questions here? Good.
Origami map is uniquely defined.
Sorry?
It's uniquely defined by the fact that you fold it everywhere.
Yes, yes. The point is that like the order of folding doesn't depend because of the angle condition. You can think about it as a folding along some path, and it doesn't matter which path you choose. So yes, it is unique. All right, so as I mentioned before, we can naturally define Kästlin weight, meaning the edge weight together with the Kästlin sign. How do we do this given the t-embedding? So let us look at the edge between two faces, white face and black face. And we take as a Kästlin sign the direction of this edge. Right, so I need to decide whether it's directed up or down. OK, I say that the black vertex is always on the right. So this gives me the complex number on this edge. So I have the length of this edge together with the direction. I claim that give me a Kästlin weight. So remember that to get a Kästlin weight, we need to check the Kästlin sign condition, which tells us that the alternating product of Kästlin signs is plus or minus 1, depending on the degree. So what does it mean? What is the ratio of two neighboring Kästlin signs? Note that if we look at two Kästlin weights, which we just defined, and I take the ratio, then the argument is nothing as the argument of this corresponding angle. So now you can easily convince yourself that this Kästlin sign condition is equivalent to the fact that the sum of white angles is equal pi, though mod 2 pi. So the Kästlin sign condition is equivalent to the angle condition modulo 2 pi. OK? OK, what else do we know about the t-embedding? Know that since it is an embedding, right, the sum of those vectors around each vertex is equal to 0. So we have an additional condition about our Kästlin weights, that around each black and white vertex, the sum of the corresponding Kästlin weights is equal to 0. Right? Now recall that the goal was not to start just from a t-embedding and define a Kästlin matrix using it, but we wanted to start from some graph together with the weights. So we wanted to start from some bipartite graph together with real-valued Kästlin matrix. And we want to find a t-embedding which give us a gauge equivalent weights to the initial weights. So we want the Kästlin matrix which we just defined to be gauge equivalent to initial weights of the bipartite graph which we had. So recall, what does it mean? It means that there exist two functions, f and g, such that we can define one of them on black vertices, another on white, that we have these, which is true, that each new weight is given by the gauge times the initial weight. So we also have this condition, which can be rewritten in terms of gauges. Right now, each new Kästlin weight is given by the initial Kästlin weight times these gauges. If we sum it around a white vertex, white face in this case, then this is the same, and we have this condition. So now this sum has to be 0. So what we're looking for, we're actually looking for two gauge functions to define the t-embedding. And what are conditions for these functions? We're looking for two functions. Both goes from the, one from black vertices to the complex plane, another from white vertices to the complex plane. And we want them to be in kernel and co-kernel of the initial Kästlin matrix, right? Just because of this condition, because if we sum around each face, then we get 0. So in the another project, we define the same embeddings using the notion of the column gauges. So we say that the gauge is a column gauge if for each vertex inside the domain, so for each inner vertex, we have those functions. One is in the kernel and another in the kernel of the initial Kästlin matrix. All right, so now given such a column gauge, we can define a t-realization together with the corresponding origami map by the following. So we say that we define a form on edges by saying that, this is the Kästlin weight, which we're looking for as a weight of the t-embedding. All right, why do I call it a t-realization, not a t-embedding? Because recall that the Kästlin sign condition, when we just take these gauges, it gives us angle condition, but modulo 2 pi. So there might be overlaps around vertex if we just take the such a column gauge starting from the initial matrix. So we need to check that the column gauge which we found give us a proper embedding. As soon as it is a proper embedding, it is a t-embedding. Okay? All right. Any questions? Great. Then I can keep going. So what is known in the general setup? First of all, with Rick, Wayne, and Sanjay, two of them are in the room, we can prove existence of those embeddings, at least in the two following cases. One of them is if the finite graph has the outer face of degree 4, then the t-embedding exists, which give us the weights which are gauge equivalent to the initial ones. And for any biperiodic graph with biperiodic weights, we also know the existence of t-embeddings. I'm going to focus on the first part today, so we're not going to talk about periodic graphs. What else we did in another project with Dima Chilkak and Binwala, we developed a new discrete complex analysis techniques on those t-embeddings. And we claimed that perfect t-embeddings reveal the relevant conformal structure for the fluctuations of the height function on the dimer model. Okay, let me say a few more words about this part, and then I will say a few words about this as well. I'm not going to go into details, but how did we prove existence for the outer face of degree 4? So it is known that there are elementary transformations of the bipartite graph that doesn't change the probability measure. So you can locally change a graph a little bit without change of the probability measure with some rules which are shown here. And we showed that the t-embeddings are preserved under these elementary transformations. And what is special about outer face of degree 4, it is known that if you start with any bipartite graph with outer face of degree 4, then there is a sequence of elementary transformations. So you can just reduce it. You can simplify it to a simple square using these elementary transformations. And now, OK, what we need to do, we need to found a t-embedding for this one. And then using this sequence of transformations, we can reconstruct the t-embedding for the initial one. OK. This is just to give you an intuition of what is special about the outer face of degree 4. And this is a result by Postnikov that for any graph with outer face of degree 4, you can simplify it. And this is not true for any other graph. So if you have an outer face of bigger degree, this is not true that you can always simplify it just to a cycle. So there might be something much more complicated, which doesn't simplify a task. All right. So finally, what is a perfect t-embedding? So far, I was talking about just t-embedding. So what is perfect? I haven't talked about any boundary conditions yet. Here they are.
Excuse me.
Yep.
If you have something that's not of degree 4, can you maybe provide some extra layer so that you end up getting degree 4?
You can, but you will define the, by adding some edges and putting some weights on it, you're going to change the timer measure on it. So it's not what you want in the beginning. Yeah, that's a problem.
So if you, what about the boundary conditions on the previous slide? Can you show existence with like non-prescribed boundary or do?
Yeah, you can do both here. You can ask them to be perfect, and this is true. Like this statement is true for the perfect t-embeddings as well, with the outer face of degree 4. You can always find a perfect t-embedding.
But without degree 4, is it easier? Like if the boundary points are known versus when they're unprescribed?
No, it doesn't help. What we know is that we can show the existence of column gauge for generic boundary conditions, but we cannot check whether at least one of them give you a proper embedding. So we cannot check that there is no overlaps. All right. So I'm going to embed the dual graph, but even more, I'm going to embed the augmented dual, which means that for the outer face, we assign many outer faces. So we assign a face to each edge of the boundary of the graph. You can think about it that we add the point at the infinity and connect it to all boundary vertices, and then take the dual graph. So, and we want to embed this augmented dual graph, which satisfies the boundary conditions. Then we call them a perfect embedding. So what does it mean? We want to map these vertices of the outer boundary into a tangential polygon, not necessarily convex. And the second condition is that note that each boundary vertex here has degree 3. So there is exactly one inner edge, and this edge should lie on a bisector on the corresponding angle of the boundary of the t-embedding. So as soon as you have these two conditions, we call the t-embedding a perfect t-embedding. And what can we prove for those perfect embeddings? Assuming that the sequence of perfect embeddings exists of our graph, plus some assumptions on faces. I will mention about them a bit later. Right now, just think that there are some assumptions on faces. And the second assumption is that the origami maps converge to a maximal surface in the Minkowski space. If we have all those assumptions, then we can show that the fluctuations of the height function converge to the Gaussian free field in the parameterization of this surface. By convergence here, actually, I mean that the gradients converge to the gradients of the Gaussian free field. But anyway, so we get the description of the corresponding conformal structure as the conformal structure of the surface to which the origami map converge. Okay, so but recall that here there are indeed like 3 big assumptions. One of them is that existence of those t-embeddings itself, and in general, it remains an open question. And also, we still need to check 2 more conditions to apply this result. So, and having this theorem, natural question is like, do we have any results where we can check all these assumptions? Yes, we do. I'm going to talk about one of them, at least one of them. I don't.
I have a question.
Yep. Sure.
What does this convergence mean? I mean, the origami map was not really living in this world, was it?
Right. So know that the origami map, I mean, in general, we had this surface in our 2+2. And now note that if I take these perfect t-embeddings, that at least on the boundary, what happened with the boundary polygon? Right? I'm folding along each edge. These two edges go to the same line. So at least on the boundary, the origami map is real. It's not true on a discrete level for the inside. But a part of the assumption here is that the origami map is real in the limit. So now I have this one-dimensional origami, and I use it. I take a graph of this origami map, and I want this graph to converge to the maximal surface in the Minkowski space. OK?
Can you explain the bisectors condition? Like, is it natural somehow to? Why is it there? For your results?
OK, it is a little bit of like great guess where things works. I can explain you for the outer face of degree 4, because in general, we simplify everything to just a square, right? And there you can choose any quadrangulator for the boundary conditions. And then there are exactly 2 t-embeddings, which are orthogonal conjugate. Yes, OK, good. And it is unique if and only if the initial one was the tangential polygon, right? Because then orthogonal conjugate vertices are the same. It's just the intersection of the bisectors. So this was an intuition like how we guessed it. Another nice thing is that as soon as you assume that there exists a gauge, column gauge, and it gives you perfect boundary conditions, we can prove that it is a proper embedding. The question is still like how to show that there exists solution which give you proper embeddings. Another thing, it was used here, it makes analysis better and easier to show the convergence of the corresponding discrete holomorphic functions, etc. A little bit rough. I can discuss with you in more details later. OK. All right. So finally, perfect embeddings of the hexagon. So the first thing which I want to say is that actually each hexagon has outer degree 6. Recall that we have these elementary transformations, which I showed before. And one of them tells that if you have the vertex of degree 2, then, OK, you need to have those weights the same. And then we can get rid of this vertex and put these 2 vertices together. So I'm talking about this one. So if we have something like this, we can change it with this vertex. So we can get rid of all vertices of degree 2 on the boundary. And this is the first thing which we're going to do. And the result we call a reduced hexagon. So now know that all these vertices correspond to just one vertex on the outer boundary of the reduced hexagon. And also know that the faces of the initial hexagon are in bijection with the faces of these new hexagon. So like these 4 faces, 1, 2, 3, 4, here are they, 1, 2, 3, 4. And the inside clearly is in bijection with inside of everything else. All right, so now for the uniform weights on the hexagonal lattice, the all Kästlin signs are 1. We cannot do the same for this one, because now we have faces of degree 4, and we have this Kästlin sign condition, which tells us that alternating product around each face should be plus or minus 1, and in this case, it has to be minus 1. So we have faces degree 4. So we need to do some gauge in the beginning. What we do, we choose every second vertex on the boundary and multiply all weights by minus 1 around it. So this, after reduction, give us the valid Kästlin sign for the reduced hexagon. And now we're looking for the embeddings of the augmented dual of this reduced hexagon. So yeah, as I said, the trick with simplifying just to a square doesn't work anymore. We need something else. So we just guessed what are the corresponding column gauge functions in this setup. So we claim that if you define the column gauge function on the black vertices in the following way, so what is written here, we take the inverse Kesslin matrix of the initial graph, and we take this linear combination where one of the arguments is one of these three boundary vertices. And similar expression for the gauge function on the white vertices. So then we claim that the corresponding t-realization is a perfect t-embedding. First of all, clearly, we need to check some conditions for these gauge functions. One of them is, this one, right? They should be in kernel and co-kernel of the initial Kesslin matrix. This is obvious because we use the inverse Kesslin matrix. So for each inner vertex, definitely these two gauges are in the kernel and co-kernel of the initial matrix. Not on the boundary, which we're happy with, because we need to get some boundary. We don't want to get 0 there. So the second thing which you need to check is that it actually gives you a perfect t-embedding. So it gives you these correct perfect boundary conditions. And thanks to the symmetry of the setup which we're dealing with, we started with a uniform case, and we have a very symmetric weight. So you can check using the symmetry of the picture that indeed it gives you the regular polygon and that those edges slice on bisectors. These two things enough to say that what we get is the perfect embedding of the hexagon. So at least we already got we just checked the first assumption. Perfect embeddings for the hexagon do exist. Here is the construction how to get them. Now, how do we check all other conditions? How we show the convergence to the to the maximal surface in R2+1? So we use the known result by Leo Petrov that for the setup of the uniformly weighted hexagon, the inverse Kesslin matrix admits the double integral formula. So we know that those guys admit the double integral formula. So all of those guys admit the double integral formula, right? This gives you double integral formulas for gauges themselves. And now you need to integrate it to get the double integral formulas for the t-embedding and for the origami map as well. So this provides us expressions for the t-embedding and for the origami map in terms of double integrals. And this allows us to do the asymptotic analysis using a classical steepest descent analysis. And using these, we can prove the convergence. OK, yeah, hold on. Before the convergence, there was one more condition, which is the some assumptions on the faces of the domain. This is a more restrictive condition than the one which we have in the CLR paper. However, it's enough. So this more restrictive condition implies the one which you need to apply the theorem I showed before. What we checked is that we checked that all edges are of order 1 over n, where n is the size of the hexagon for n large enough. And we also checked that all angles are bounded from 0 and pi of those faces. And as I said, yet again, this is more restrictive than what is needed to apply the theorem, but it implies what is needed. Yeah.
Does it degenerate at the boundary?
Sorry?
Does it, like, the face is degenerate at the boundary?
I will show the, yes, I will show a picture in a second. Here it is. So that was the condition on the faces, and also we proved that the corresponding origami map, the graph of the origami map, converges to the maximal surface in R21. Here is how it looks like. And let me give few comments about this picture. So what is this? This is the t-embedding of huge size, and this is the corresponding origami map, how it looks like. So let me say a few, this is not visible, but let me say a few words about this picture. So what's happening, note that here we have some frozen parts, right? And there is no fluctuations. So what happened with all this frozen region from the initial hexagon, initial drawing of the hexagon? All this area maps to a point. So this is what's happening with all frozen regions. So they simply map to a point. So this hexagon is not the same as this hexagon. What happened is that all this liquid region inside the Arctic Circle mapped to the hexagon of the t-embedding in our embedding. So we redraw a graph, and it changed the structure. We don't have these frozen pieces anymore. They all map just to a point. And yeah, I mean, this is how the origami looks like on the large scale, you can believe that indeed it is goes to just a real line in the limit. And the results which I mentioned before tell us that all assumptions of the CLR paper hold. So we can use this to say that the fluctuations of the Gaussian free field for the uniformly weighted hexagon converge to the GFF in the conformal structure of this maximal surface in R2+1. OK. I still have 10 minutes, right? Are there any questions about that? All right. If not, then I will say a few words about the Aztec diamond, which we heard a lot about today already. So thanks to the first speaker and also the second speaker, I don't need to say much. So very quick reminder, Aztec diamonds are domain of this. We have this coloring. We know that the height function has a scaling limit. We know the fluctuations result. They converge to the Gaussian free field in some conformal structure. And in the uniform case, if you deal with the corresponding reduced graph, we already actually saw this picture already, if you remember. This is actually the outer face of degree 4. So for the Aztec diamond, you can use this trick, and you can use this shuffling algorithm to reduce the graph to just a square. And the spider move for urban renewal move correspond to the following equation for the t-embedding itself. And you probably cannot see it, it's too small, sorry for that. But what is written here, you can recognize a discrete version of the wave equation in this equation. And this is what Dima and Sanjay used, first of all, to show the existence of those t-embeddings, and also to guess the limit of t-embedding. So you can say that, OK, if we have a wave equation here with some boundary conditions, the limit should be the corresponding continuous solutions of the wave equation with the corresponding boundary conditions. This allows them to check that indeed what you get is a limiting. There is a similar equation for the origami map, and you can check that the limit gives you the Lorentz minimal surface, and that the conformal structure which they get there in agreement with the known one, which we already know, right? So, however, like they didn't check the all assumptions, so they didn't check the assumptions for the convergence plus those technical conditions which I was mentioning. So in another project with Thomas and Matthew, we know that actually this allows us to rewrite the t-embedding in terms of edge probabilities around the corresponding face. And again, we use the same technique. Those edge probabilities can be written in terms of inverse Kästlin metrics. We know already asymptotics from those results, and we can check all the conditions. Right. So this is a small remark to the previous project, and I want to actually say a few words about the future project. So Alexei was mentioning more interesting setup. What happened if you have these gas phases, right? If you have these periodic weights, what can we say about t-embeddings? Not much so far. This is work in project. However, I want to show you the nice picture. At least we can prove that gas phases for the t-embedding converge to the points as well. So all frozen regions are points for the t-embedding in the limit, and gas phases are points for the t-embedding as well. We cannot prove any convergence to GFF. That would be nice, but not yet. The analysis of CLR is not enough to deal with gas phases, and we cannot do it yet. But we can study the t-embeddings of Aztec diamond with periodic weights, and we can say at least something about the corresponding t-embeddings. Yeah, that's it. What I wanted to say. Thank you.